Okay, so today we're going to look at the inverse matrix. So if you have an inverse to anything, so first we could write the inverse as, so if we had, say, the letter X, the inverse of X is, you can write it like this, so to the power of -1, or you could say it's like 1 over X. So when we say that, really if you multiply something by its inverse, it's like you're dividing. So say, for example, if I had 3 to the power of -1, that's like the same as having 1 over 3. So if I multiply something by its inverse, by an inverse, you can see it's like you'd be dividing. So say I had 6 multiplied by the inverse of 3, it's like I've got 6 times 1 over 3, so it ends up being 6 divided by 3. So it's like a dividing thing. So in matrices, we can't essentially divide. The way we do division in matrices is we multiply by the inverse. So we're going to look at finding the inverse manually for a 2 by 2. So you need to know how to, you might just write that there, you need to know how to manually do it, and just for a 2 by 2. The rest we do using a calculator, okay? So it's just the 2 by 2. So the first thing we need to learn is part of the inverse formula is this determinant. So if we've got, so we're going to look at that first. So here you can see we have a 2 by 2 matrix. And you can see I've got those separate elements I've got 4 elements inside that matrix. So here's a 1, 2, 3, 4. So when you're finding the determinant, what you actually do is you take this number, the number in that position, you multiply it by that. So you can see we've got A times D. Then you you subtract B multiplied by with C. So there you go. So you can see in this example we've done here, we did 2 times 5 there, and then we subtracted 3 times 3. So that'd be 10 minus 9, which equals 1. So the determinant of that matrix is 1. All right, so if we've got our example here, if we're going to find the determinant of H, so we might write DETH, the determinant of H, is going to be that 2 times 3 minus 4 times 2. So that would be 6 minus 8, so equals -2. So your determinant can be a negative number or a positive number, doesn't matter. Okay, so we've worked out this is our basic rule for a 2 by 2 for the determinant. And it says we've got a few other examples here to work out. So if I was doing the determinant of this first matrix here, it'd be 3 times -3 minus 4 times 2. So that would be -9 minus 8, so that'd be -17. And then this one, it'd be 6 times 2 minus 3 times 2. So we've got 12 minus 6, so that's 6. And then the last one, we've got 4 times 6 minus 8 times 3. Now, 8 times 3. So that one equals 0. Now, this is what we're going to lead into. When the determinant equals 0, that does tell us something. So when here, and you've got the notes down there, when the determinant equals 0, we call this original matrix singular. So that's an important, so if you write, then when the determinant equals 0, the matrix is singular. Okay, so we'll learn a little bit about that in a minute, but just for now, determinant equals singular, and you might write underneath, which we'll understand a bit later, it means there's no unique solution. You might write that too. So unique solution is when the determinant equals 0 as well. Okay. All right, so a singular matrix is when the determinant equals 0. So which one of these following matrices has a determinant worth 0? So here you can just work out your determinants. So in your calculator, you can actually write DET and do a curly bracket, then type your matrix in, and then press enter, and it'll tell you. So this one would be 0 minus 1, so it's going to be -1. This one's determinant would be 1 minus 0, so it would equal 1. This one would be, now careful, this one's determinant would equal 1 times 6 minus 2 times -3. So remember, what's a minus? Take away a minus? Plus. So that one's determinant's going to be 12. All right, this one would be 12 minus 12. So this one's determinant equals 0. So we know this is a singular matrix, if I could spell. So this one's a singular matrix. Okay, and then that last one would be negative, the determinant would be -8. Okay? Okay, so as I said, we needed just to know that determinant, and that was because we need to use it to find the inverse. So here we're going to be looking at finding the inverse matrix. So the inverse matrix, you can just do it in your calculator by raising a matrix to the power of -1. And obviously an inverse matrix must be square, because remember back we said you can only raise a square matrix to a power. So we can only get an inverse matrix if it's square. But what we have to know how to manually calculate an inverse matrix of a 2 by 2. So once again, we've got this 2 by 2 where we've got all the elements in this. We've got the 4 elements. So what you can see here, if you look at the formula, so this is the formula for inverse. Okay, so if you look at that formula, you can see down here highlighted in the blue, that's the determinant. So you can either write the actual formula for the determinant, or they might, down here underneath, they just wrote, you could put the determinant there. So that's the first part of when you're calculating. Now also you will notice that when you're working it out manually, can you see that these two numbers, so A and B, they get swapped in positions. So they've swapped, and if you look at the spot in B and C, they just become negative. Okay, so we'll do an example in a minute. So you can see that's the formula for it. So if you look, because we've got 1 over the determinant outside, so this bit outside, that's like a scalar number, yeah, on the outside. If that determinant equals 0, you can't have 1 divided by 0. That's undefined. Okay, if you try to do 1 divided by 0, it's undefined on your calculator. So you'll see if you get a determinant of 0, you cannot find the inverse. It's impossible. So you might write that as a little note. So if the determinant equals 0, you cannot find the inverse matrix, yeah? So sometimes that can save us a lot of time of calculating. We just work out the determinant and we can't, if it's 0. And here's, like we said if the determinant equals 0, the matrix is singular and there's no unique solution. So we've already wrote that out. So we know that. So that's just important to remember. Okay, this other little fact down here that they've put here, we've got that if you multiply something by its inverse, you end up with the identity matrix in matrices, because it's like a number 1. Because if you think about just in normal maths, if you had 3 and you times 3 by its inverse, it would be 3 times 1 over 3. So you can see that ends up being 1. So in matrices, it's the same. So if you multiply matrix A by matrix A's inverse, what you end up is with an identity matrix. So for example, if A was a 2 by 2, and obviously the inverse will be a 2 by 2, your identity matrix will be a 2 by 2 identity, like that. It'll end up being that. Identity is like a number 1. So there, that's why we get a number 1. Okay, if you have a matrix any bigger than a 2 by 2, we're not going to ask you to manually do it. You just pop it in your calculator. So you just raise the matrix to the power of -1 and you'd get the inverse. Okay, you don't have to do any calculations for anything bigger than a 2 by 2. Okay, so we're just going to work through this example. So if you have a look, here's the original matrix. So we're first finding the determinant because we need that for the formula of inverse. So we're going 2 times 3 and we're minusing 4 by 2. So we end up with a determinant of -2. So remember our formula for inverse was 1 over the determinant. So there I've put it in. There's the determinant being added in. And remember, we're going to swap these two numbers around. So you can see 3's come up here and 2's gone there. Okay, and then we made these other ones, these two, become negative. And you can see they've become negative when we've done the inverse. Okay, so then what they've done is, because this is like a scalar number out the front here, we have just multiplied that out. So I'm going to actually, so we've done that to a decimal number, but I want to just show you how you can do it. You could have left it in fraction form, and we just might leave it like that in case our multiple choice have that option. So this could have been, if I multiplied that scalar out here, I'm multiplying that out, I could have just said it's like 3 over -2. Now -4 over -2, and that becomes that's why it became a positive. And then I could have had, it would be -2 over -2. So whatever the determinant ends up dividing all those numbers underneath. Okay, so that's how we could have left it like that. So if I left it in fraction form, this one should have been negative. Sorry. Yeah, so make sure you fix that up on your notes. That should have been -2 or -1, sorry. All right, so we get -1 there. Okay, so they've just done another example there. So obviously, if you've got decimals and they don't ask you to show how the inverse is done, you can go straight into your calculator. So when you've got decimals like this, you can still do it, but I probably, when it just said find the determinant of A, now you could always on your calculator just typed in DET, put a curly bracket, put that matrix and done that, and you would have ended up with 0.5. And then when they ask for the inverse, the same thing, you can just type it in your calculator. And here we're just going over the fact that if you times something by its inverse, you're going to end up with the identity matrix. Only square matrices have an inverse, and that makes sense because it's the power of -1. We only can raise square matrices to the power. Okay, and not all matrices have an inverse. So you might just want to write another little note there, like what we said. If the determinant equals 0, no inverse can be found. Okay, so in case you're looking there in your notes, you'll see that. Okay, so here with this one, they're asking me to show the matrix A and B, show that matrix A and B are inverses. So really, what they're saying that is this is actually matrix A, the inverse. So how do we show it? We find the inverse of one of them. So I'm just going to find the inverse of A. So I'm going to find inverse A. Okay, so the rule is 1 over the determinant. Remember, we would swap those two positions and make the other two negative. So I'm going to do that for my example. So it'd be 1 over the determinant. Now the determinant is 6 times 2 minus 3 times 2. Now I'm going to swap those two positions and I make the other two negative. Okay, so once I do that, I keep tidying that up. That would be 12 minus 6. And I'm just writing these out again. Okay, so 12 minus 6 is 6. So 1/6 over outside that. So now I'm going to multiply that scalar out. So remember I said it ends up being just everything over the determinant. So, and 6 over 6. So we can actually simplify that, can't we? Some of them we can simplify. So 2 over 6 would simplify to 1 over 3, yeah? And negative 3 over 6 is the same as negative half. I'm just simplifying these fractions. So this would be negative 1/3 and this would be 1. Now, does that look like B? Yeah. See how this is what matrix B is? So therefore we know, yeah? So this was inverse A. So we could say therefore inverse A equals matrix B. So you're only going to get asked for a 2 by 2. Anything bigger, you just pop it in your calculator. They've stored them in the explanation here. What I would have done on my calculator for this one, if I was finding the inverse of A on my calculator, all I would have typed up was that matrix, and all you need to do is raise it to the power of -1. So if you're looking for that, remember when you want to raise it to the power, use that power key, yeah? If you had to just find the determinant of A, you can just type DET, curly bracket, and then do the matrix, and that would have found you the determinant of A, okay? Alright, so here's a couple of exam questions. So this is what you were asking before. Do you have to show you working out? You don't, but in this one, this is why you have to know how to manually work it out. So it says the determinant of this matrix is equal to 9. So the way you would find that determinant, you'd go 3 times x minus 2 times 6, and they said it equals 9. So if you end up with this expression here, so if you're not too good on your algebraic like solving, that's fine. You can just do solve, and that's okay. We're not testing you on that skill, so pretty much. But if you end up with that, what x equals, so okay, so this one we found the inverse. We let the same spot equal the same spot, and then that's what we've put here, and then we've done solve. But I don't believe this will be on the exam. Okay, so then we found that k equaled either 0 or 2. So what I did is I put in the original matrix A 0 and 2, and then went to find the inverse. Now because this inverse does not look like the original, which is what they're saying is equal to, therefore it has, when it's 2 it does. This looks exactly the same, so 2 is the answer. A and B are square matrices such that AB and BA equal the identity. So if you multiply two matrices together and you get the identity, it means they must be the inverse of each other. So which of the following is not true? So if you know that they must be the inverse, so B must be the inverse. So what that just told you here, B must equal the inverse of A. Alright, so which one's not true? So if you multiply these two, if we look at this first answer here, if you just do that, you're going to end up with the identity matrix. And then you times it by A, so anything timesing identity is like a number 1. So if I go 1 times A, yes, I'm going to get A. So that is a true statement. Now, if you multiply A by B squared, So really what you got here, and then by A, you've got two inverses here. So remember B is the inverse. So you'd have two of them, and you're dividing, and you've got two A's. So if you've got two A's and you're dividing by two inverses, that means you're going to end up with the identity. Does that make sense as well? So I'll just show you what I meant by that. So remember, B equals the inverse. Remember, and I said B's like saying, it's like dividing by A, okay? So this one, I could say I've got this A, and it's multiplying up the top with that other A, and this B squared, they're like having the inverses down the bottom. So they would all cancel each other out, and wouldn't that give a 1, which is like the identity matrix? So that statement is true. Now, which one does B must equal A? That is not true. Are they equal? No, it's the inverse. So already I think that that is not true, and the rest of my statements should be true. B is the inverse of A, that is correct, and both A and B have inverses, that is correct. So C is the answer.